Hi, everyone. Okay. Um, can you see my screen, Ben?
Yes, I can.
Okay, great. So today I'm going to talk about analyzing education discourse on social media with topic models. I'm going to focus specifically on the STM package, which lets you estimate correlated and structural topic models. To give you just an idea of what's to come, first I'm going to start off with a bit of context on the project from which this data comes. Then I'll give a very brief introduction to topic models and the STM package and the workflow that it supports. And then we'll go through an example of this workflow answering kind of two key questions. What is the topical structure of education thought leaders, social media posts, and how likely are government agencies to discuss a couple of the topics that we find in answering the first question. And then I'll conclude with talking about where you can find extensions to the package. Okay, so actually I should first start out by saying the research here was supported by the Bill and Melinda Gates Foundation, but nothing in this presentation necessarily reflects policies or positions that the Bill and Melinda Gates Foundation takes. So the larger project here that we were interested in was, can we capture the extent to which specific educational priorities make up social media discourse as a whole? And then if so, how are different actors engaging these topics and who exactly are the actors? And so we've been looking across Twitter, Facebook, and Reddit at a bunch of different types of actors. So this is everything from major individuals in education policy to, as I mentioned, government agencies to schools and school districts. So this is very, very varied. And in the presentation, I'm just going to use Facebook posts from a list of thought leaders that we manually came up with. This is our education researchers at NORC in conjunction with the folks at the Gates Foundation. So topic modeling is for the most part, a set of unsupervised methods of kind of figuring out what is being discussed in texts. And so the most popular approach is latent diversity allocation. It's called LDA. And basically, you give it a set of texts, and it says, okay, within these documents, each document is distributed in this way across these different topics. It's composed of a different amount of the topics. And actually each topic is a distribution, a unique distribution across the words found in the documents. But a key problem with LDA is actually that it doesn't allow you to model correlation between topics. And this is something that we intuitively would recognize that should occur, right? Because if people are more likely to talk about one topic frequently, they're also more likely to talk about another topic. And so structural topic models build on the correlated topic models even further by allowing you to incorporate covariates. And so there are two different types of covariates that it allows you to incorporate into the model's prevalence, which gives a topic frequency so that you can look at things like, what factors are associated with talking about, topic X. Or content, you can say, given that a topic is going to be discussed, what is associated with using like certain words versus other words. And so the STM package allows you to estimate correlated topic models and structural topic models. I'll point out in the code kind of where they diverge. We're going to focus on a structural topic model example, but the code is running one versus the other is very simple. You just omit certain things and it will collapse during the estimation process into correlated topic models. And so the analytical workflow for the topic models generally, and then the STM kind of package provides functions to support this, is as follows. First, you take your text and you pre-process them and process the metadata that's associated with the text, however necessary. Then you join these different types of data together into a corpus. You estimate the model, and then you want to evaluate the results and see, do the topics that the model identifies actually cohere together? Do they make sense? And so you do this by looking at like the top words associated, most distinctive of each topic, and then quotes or full documents associated with each topic. And that way you can do these work well, and you may need to iterate through these first several steps. You more than likely will. And then finally, you can look at the statistical relationship between topics and the covariates that you are interested in. And so just to give you an idea of what the data that I'm going to input into the model looks like, here are the Facebook posts. I just put it in a data frame. STM is really flexible and kind of the data structures that you can feed into it. And so we just have text. I did a bit of preprocessing, for example, to take out URLs at this point. So we have a column that is the text, and then other columns that then just think type is like the type of actor that the author is, and then you have likes, comments, and shares. There are roughly 94,000 posts that we're going to start with, and the main covariate that we're going to care about in this example is gov agency. You can see it at the bottom, and basically this is just an indicator variable. So it's true if the type above equals government agency, and it's false otherwise. And so now that you kind of have an idea of this data frame that contains both the covariates and the text itself, we can move on to preprocessing. And the first function that STM provides to preprocess your data is called text processor. And so here you give it the documents, which again was just a text clean column in the data frame, and the metadata. Since we have it as a data frame, you just give it the entire data frame, and then you can specify what you want done to the text. And so you can do things like lowercase, removing stop words, numbers, punctuation. You can stem. This is a highly flexible function. And so there's a lot of things that you can specify, but two things I think are particularly important is you can specify custom stop words and also custom punctuation, and that can be really useful. And so when you execute this function, you see it updates you as it goes through each step of the process. So another task that you might want to do in pre-processing is removing really infrequent words. But different definitions of what infrequent means can change your corpus in different ways. So STM provides the plot removed function to be able to look at the effect that these different thresholds have. And so for plot removed, you provide the documents and then your set of lower thresholds that you want to look at. So for here, we're just going to use 1 to 200 by increments of 1. And the output, which I have here on the next slide, it gives you 3 different plots. It's the number of documents that are removed at each threshold, the number of words that are removed at each threshold, and the number of tokens that are removed with each threshold. And so here's what the output looks like when you plot that object. And basically what you want to do here is go through and you want to remove infrequent words, but you don't just want to totally kind of do away with your corpus. And so this is you can go between these 3 and kind of triangulate what a good number might be. And this is something that you can iterate on in trying to improve the quality of your models. But for now, we're just going to choose 10. And so now that we have the threshold of kind of the words that we want to remove if they occur fewer times in our corpus than 10 times. So we use the prep documents function. And what this does is when you remove words and it affects the documents and things that are removed, it ensures that the text and the metadata are kind of all updated together. And so you're able to match correctly your text with its own metadata. And so this is really useful because you can't really interpret anything if the indexing gets off. And so this is, again, like I said, the prep documents function. And so you just tell it the documents, the vocabulary, which is a part of the output of the text processor, and the metadata, and then you give it the lower threshold. And after you execute it, it provides a nice summary here, tells you what's going on. So we lost, for instance, 416 documents because after it removed the infrequent words, the documents were empty. And so, so now that we've pre-processed, the question that we have in moving to, before we can estimate our model, is how many topics are there? And this is a problem with topic models because the number of topics is something that we frequently want to know. We don't know beforehand. Um, and but we have to tell it the number of topics. So STM provides search K, which basically allows us to say across this range of potential topic numbers, how well does the model perform? And it includes several heuristic measures. So in the search K function, we give it the documents, we tell it the vocab, and so this highlighted spot here, prevalence, this is where the STMs diverge from the CTM. So if you don't include prevalence here, then it will estimate a correlated topic model. But in terms of code, that's the kind of main difference. And so we tell it prevalence, we do the tilde and just give it government agency. If you want to include more than one covariate, which you can, you just provide the kind of formula notation. And then we tell it K, the number of topics. We give it this range that we want to estimate. And so we're just going to say, we think there are between 5 and 20 topics. And then I ran this on the server, so I gave it 15 cores, one for each potential topic number. This doesn't work on Windows. And we're going to give it a C just for reproducibility. And so when we run this, we can plot the output and we get this. So there are several metrics, and I'm not going to talk about all of these for time. They're well documented in the vignette and the package documentation, but I'm going to talk here about the two on the left, because I find it held out likelihood and semantic coherence in my work typically are the most consequential. So for held out likelihood, basically we say, hold out a proportion of words within a set of documents, train that model, and then use document level variables to evaluate the probability of the held out proportion. And so we want to maximize this metric. And we see that after the first several topics, it slowly kind of increases. And so basically a larger number is better. And semantic coherence, we also want to maximize. And this captures the idea that we want words to frequently occur within topics together, and we want the topics to be pretty distinct from each other. And so here it decreases, and then it decreases and then increases pretty slowly until 16, at which point it just drops down dramatically. And so we're going to choose 16 here. This is certainly something that you would want to iterate on if you were estimating your own. But between these two, we're going to choose 16. And so the STM function is what we now will use to estimate the actual structural topic model. And the syntax for it is quite similar to search K. So we give it the documents, the vocabulary, the prevalence, again, just the tilde and the covariates, the data, so the metadata, so it knows what government agency is. We tell it that K, the number of topics, is going to be 16. So we run this, and now we're at the point where we want to know, how well it's performing. We want to be able to validate this. Is it actually producing topics that makes sense? And so the label topics function is one way you can do this. It provides the kind of the keywords most highly associated with each topic. And so what you do here is you give it the STM model. You can specify which specific topics. We're only going to look at 2 topics here. You can leave this blank and it will give this information to you for all of the topics. And then n equals 6 is just the number of keywords that we want displayed. The default is 7, and 7 made it go off of the slide, so I just decreased it. And so what you see here, within each topic, there are 4 highest prob for X, lift, and score. They're just different ways of calculating kind of what is distinctiveness, like different ways of calculating what are the most distinctive keywords of each of these topics. And for topic 8, we see game, basketball, football, tournament. And so this does seem to be kind of at a high level, pretty coherent around sports. And topic 12, we see tends to be about what I'm going to call education or research and evaluation. Right? So we see research, AERA, develop, learn. Yeah, and so another thing that you would want to do is look at longer quotes in the actual documents. And so you can use find thoughts function to do that. We're not going to do that for space considerations here. But now we get to kind of the final step here, and we use estimate effect to be able to look at the relationship between the prevalence covariate and or the prevalence, topic prevalence and the covariates. And so in the estimate effect function, 1 through 16 just specifies that we're wanting to run this for all topics. And we use the formula notation to specify the covariate. So we give it the STM object and then specify the metadata. And so basically this runs 16 different models, and it includes regularization. You can customize the type of regularization that it uses. So if we run summary on this, I'm doing this just for topic 8. We can see here that there's a statistically significant negative relationship between the author of a post being a government agency and how much they're going to talk about sports. So they're not very likely to talk about sports, but we can visualize this. It offers a nice tool for this. And so for plotting this, we have to switch it to a factor. It was illogical, and this is just in this particular plot function, it has to be a factor. And so we give it the output of the estimate effect. We tell it which covariate we care about, which levels of the covariate we care about, which, because this is an indicator variable, it's just true and false. And the other things here just kind of customize the appearance of the plot. And so what we see here is that government agencies, we can see here, are less likely to be talking about sports, and they're going to give more attention to research and evaluation. Yeah, so this is just a nice little graphical interface to the results of that. And just so kind of what we've done at this point and here in closing is that we've seen that just kind of the range of functions that STM provides to support this workflow. We found that there seem to be 16 topics that at a high level that are being discussed within this corpus, and that government agencies are more likely to devote attention to research and evaluation as opposed to sports. And so STM is great because, like I said, at the beginning, it implements models that address kind of key conceptual issues in topic modeling. So this is correlation between topics, and then also being able to answer questions about how attention given to topics varies systematically. It provides utilities for all components of the topic modeling workflow, and that's something that I really appreciate. And then it exists within a well-supported ecosystem. And so to really get an idea of all of the tools that support and extend the structural topic model package, you can go to structuraltopicmodel.com. There's a bunch of documentation. There are even Shiny apps that help you, graphically interact, if you would like, with the STM package and produce kind of nice output. And the GitHub repo is actually a really good source of information where you can get. And Brandon Stewart seems to be quite active in responding to questions and issues. So I will stop here. Thank you.
Thank you, Brendan. And would the script for all of this be in your GitHub repo?
I can put it there. I have not yet.
Fantastic. And another question is, what resources should a beginner look at for learning more about CTMs and STMs?
So I would go to the Structural Topic Model website. It's what it does. You can see they keep track of like papers published in peer-reviewed journals, so it gives you nice applications, but then it also provides links to the vignette. The vignette is incredibly good. And so that's the first place that I would start, or I guess the two places would be the vignette and then the structuraltopicmodel.com, which will send you a link to, will give you a link to the vignette.